Hello everyone, this is Maushmi. Today I am here with some interesting problems on electrostatic potential and capacitance. But before I begin, I would like to thank you all for your support. Please subscribe our channel and lots of videos are there on different topics. Online registration procedures are going on. You can register. So let's begin the first problem. A medium having dielectric constant K greater than 1 fills the space between the plates of a parallel plate capacitor. The plates have large area and the distance between them is D. The capacitor is connected to a battery of voltage V as shown in figure A. Now both the plates are moved by a distance d by 2 from their original positions as shown in the figure B. In the process of going from the configuration depicted in figure A to that in figure B, which of the following statements are correct? So this is basically figure A. This is figure A and the one besides it, this is figure B. So you can see the figure. We need to check whether which of these statements are correct, or could there be more than one answers for a single one. Now let us try to understand the problem. We have a parallel plate capacitor in which the plates are separated by a small distance d. V is the potential which is provided by a battery to the two plates of the capacitor. Now, if the plates are moved through distances d by 2 each, then we need to see which of these following factors or which of the following options will appear correct. So now if we try to write down the capacitance for the initial figure and then the capacitance for the final figure, we can have a comparison between the two capacitances. The options that we need to check are: the electric field inside the dielectric material is reduced by a factor of 2K, the capacitance is decreased. So it tells us, these options tell us basically that we need to find out the electric field in the case of the two figures. We need to find out the capacitance. We need to check whether the voltage between the capacitor plates is increased or decreased corresponding to the two figures, and also we need to find out the work done in the process and check whether it is dependent on the presence of the dielectric material or not. So let's begin first with the electric field. So now, in the first case, when the plates are separated by a distance d, if we try to write an expression for the capacitance of the parallel plate capacitor, let us consider that as the initial capacitance. The initial capacitance, say Ci, is equal to epsilon naught A by D for the plate separated by a distance d, and if the area of each plate is capital A. This is if the material between the plates is free space, that is air or vacuum. But since here in this question it has been told that the two plates are separated by a dielectric material of dielectric constant K, so the constant K comes in the denominator. Sorry, this comes in the numerator. So we have K epsilon naught A by D. Now this is for the initial, that is for the figure A. This is all for figure A. Correspondingly, if we try to write down the capacitance corresponding to the figure B, let us take the capacitance as the final one. This is CF. We have this as epsilon naught A by D. This is for the material to be free space in between the two plates, and since we have the two plates which are moved through distance d by 2 each, so with this d we have an additional factor of d by 2 by k, and another for the other part also it is d by 2 by k. So sum of the two will give us 2d by 2k, which is nothing but d by k. If we sort this out, we get this as epsilon naught Ka by d is taken common, and we have this as k plus 1. So this is the final capacitance corresponding to the figure B. Now having the capacitance, let us try and write down expressions for the charge in each case. In the first case, the charge is Qi, the initial charge. Charge is equal to Cv, that is Ci, and the potential, that is V. So putting the value of Ci here, we have this as K epsilon naught A by D whole into V. So this is the expression for the charge. Now the electric field in this case, Ei, this is nothing but sigma by epsilon naught, sigma by K sigma by, the formula is sigma by epsilon naught, and putting in the value of sigma, sigma is nothing but charge per unit area. So this is charge Qi by unit area, that is epsilon naught A. We have this. So this, if putting in the value of Qi here, we'll get this as Ei, which is equal to K epsilon naught A by D into V. It is substituted here. Ultimately, we'll be getting this as K epsilon naught A by D whole into V, and in the denominator we have epsilon naught A again. So the formula turns up to be K times V by D. So this is the thing that we are getting. Okay. So this is for free space. Now, since there is a material of dielectric constant K, so here the term, the dielectric constant will come up. So if you take a note on this, we have this and K in the denominator. Ultimately, the K in the numerator will get cancelled out, and we get Ei as equal to V by D. So we are having an expression for the electric field intensity for the initial case, that is corresponding to figure A, and that is Ei equals V by D. So this is the expression. We also have an expression for the capacitance, which we will be requiring since these two options demand the electric field and the capacitance. So these are the fields and the capacitance corresponding values. Now let us apply the same case in case of the second one. We have Cf. Let's calculate Qf now. Qf is nothing but Cf times V. Then let's substitute the value of Cf. We have this as epsilon naught Ka by D times K plus 1 whole into V. This is Qf. We have E suffix f, the final field. The final field here in the presence of dielectric, this is equal to sigma by K epsilon naught. So sigma here is nothing but Qf by Ka epsilon naught. Sorry, this is epsilon naught. Putting in the value of Kf from the above expression, we get Ef is equal to epsilon naught Kav by d times k plus 1, and in the denominator we again have Ka epsilon naught. So this gives us Ef as equal to, you can see Ka epsilon naught all get cancelled out and we are left with 1 by k plus 1 and V by d. So what we can see is that Ef is equal to 1 by k plus 1 times V by d is nothing but Ei. So we can see here that the electric field is inside the dielectric material is reduced by a factor 1 by k plus 1. So we see that the first option doesn't hold good. Now testing the second option. Let's look at the second option. We have here, this is the case for the capacitance. So comparing the capacitance in this case, what we can see is that, let's compare the capacitance. We already have the values of Cf and Ci. Let's divide the two values. We can see that Cf is nothing but epsilon naught Ka by d times k plus 1 multiplied by Ci, but in the denominator, so we have d by k epsilon naught A. So you can see that some terms get cancelled out and we are left with Cf by Ci is equal to 1 by k plus 1. That is Cf, the capacitance is in fact reduced, or it is decreased by a factor of 1 by k plus 1. So this option holds good. The second option holds good. Now time to check the third option. You can see that the voltage between the capacitor plates is increased by a factor of k plus 1. We see that the voltage has not changed in either of the cases. So the third option is not true. And looking now at the fourth option, we need the work done. So let's find out the work done in the two cases. So work done is nothing but we need to calculate the work done as the change in energy. So for the initial case, the stored energy is half Cv square, that is half of Ci V square. And for the second case, it is half of Cf V square. So let's find out the difference. The difference in energy basically appears as the work done. Let's find out the difference and see how the work done depends on, or whether it really depends on or does not depend on the presence of the dielectric material, or we can say on K, that is the dielectric constant. So let's have a look at that. So for that we need to retain the expressions for capacitance. So work done is nothing but the change in energy, half Ci V square minus half Cf V square. So we have half of, so Ci minus Cf, or you can say the final minus initial. So just have a look at the two expressions. So the final is getting reduced, so we'll have just the opposite. That's it. We have this as Cf minus Ci square. So this is half and V square. Let's keep it as it is. We do not have the value of V square in fact. This is CF minus CI. Now what is CF? We have CF as epsilon naught Ka by d times K plus 1 minus Ci, that is Ka epsilon naught by d. So this is the thing that we have here. Let's work on this. We have this as some terms can be taken out common. We have epsilon naught Ka by d coming out common. We are left with 1 by K plus 1 minus 1 in fact. So finally what we see that the work done is equal to, this is epsilon naught Ka by d, 2d in fact, and we have V square, and here we have K plus 1 as the LCM, and we have this as minus K. So this is what we have, or we can simplify this further and write it as minus epsilon naught K square AB square by 2D times K plus 1. So what we can see is that the work done is dependent. It is a function of K. So work done is dependent on the dielectric material. Between the plates. Or we can say it is dependent on K, the dielectric constant. So we see that the option D is also not correct. Now, moving on to the next problem. A 5 microfarad capacitor is charged fully by a 220 volt supply. It is then disconnected from the supply and is connected in series to another uncharged 2.5 microfarad capacitor. If the energy change during the charge distribution is x by 100 joules, then value of x to nearest integer is. So we have a capacitor. Let's take it as C1. This is equal to 5 microfarad. It has been charged to a potential of 220 volt. Now this is disconnected and connected in series with another uncharged capacitor of capacitance C2, which is equal to 2.5 microfarad. Now if the energy change during the charge redistribution is given as x by 100, we need to find out the value of x. So what is the energy change here? So C1 and C2 are connected in series. So we need to first find out their equivalent capacitance. In series connection, it is given as 1 by C eq, equivalent capacitance, which is equal to 1 by C1 plus 1 by C2. So this is nothing but C2 plus C1 by C1 C2. So we have C equivalent capacitance as C1 C2 by C1 plus C2. Now the energy change, this is given as half. Energy is nothing but half CV square. So half C means it is the C equivalent here, and V square. So what is V square here? Initially we had V, the potential was V1 equals 220, but later on it was disconnected, which means that for the second part of the problem, the potential is 0. So the change in potential is nothing but V, which is V1 minus V2. That is, indirectly we can say this is equal to 220 volts. So this is CV squared. Now let's put in the values. Half of CEQ is nothing but C1 CT by C1 plus C2. So C1 C2. 5 microfarad. Let's convert it to farad. We are doing this problem in SI units. This is C1 and then C2 is again 2.5 times 10 to the power minus 6 by, we have C1 plus C2, sum of the two. So this is nothing but 7.5 times 10 to the power minus 6 farad and V square, that is 220 square of that. So if we work on this, you can see that it comes out to be around this is almost of the order of 40333 times 10 to the power minus 6 joules. Now let's arrange this a bit. We have this as 40 into 10 to the power minus 3 joules. So if you compare this relation with the expression that has been given, here we have been given that the energy change, this is by question, given in question. By question, the energy change is equal to x by 100. So we may write 40 times 10 to the power minus 3. This is in joules, is equal to x by 100. Let us bring this part in this form. We have this as 4 by 100. This is equal to x by 100, which gives us x as equal to 4. This is the nearest integral value of x. So a wonderful problem in fact. Thank you.